Whoa. Sorry, I was trying to be the next Nathan Chen in figure skating, but since I'm a science nerd, I've given up my short-lived career of figure skating to tell you all about spin. In real life, we all think of spin as angular momentum, or the quantity of rotation in an object produced by an external force. But can we ask the same question for elementary particles such as electrons? Are electrons really spinning? Well, they're really not, and we can prove this using the Stern-Gerlach experiment.
In this experiment, there's a certain orientation of magnets that produce a unique magnetic field. But for now, let's just think of it as a spin separator. This magnetic field is a 2D representation of the magnetic device that we saw earlier. When a magnet is sent with its north pole up and south pole down, the magnet is deflected upward as soon as it exits the magnetic device. When the poles are inverted, the magnet is deflected downward. So we can say that the deviation of the magnets depends on the orientation of its poles. So if we send infinitely many magnets with a random orientation, they will arrive anywhere corresponding to the magnetic field's behavior.
But what if electrons are sent? Well, they're deflected as well, but they reach the screen only upward and downward, never in the middle. This proves that each electron behaves like a magnet, but with only two possible vertical directions, in which we call spin down and spin up.
Now we can argue that the electron is not actually spinning as you see objects spinning in real life. While objects have a defined size, scientists are not really sure about an electron's size. In fact, they actually appear to be point-like particles, which do not have angular momentum. If an electron had a definite size and would be spinning like we see most objects do,
It would have a surface that would have a velocity 1 million times the speed of light. Which, according to Einstein's theory of special relativity, anything that could travel faster than light would move backward in time. And at the same time, special relativity states that this would require infinite energy. We can then prove that if the electron is a point-like particle, then it cannot have angular momentum due to spinning about its own center of mass because the entire object is on its rotational axis. The only directions that the electron can undergo is plus 1/2 h-bar and minus 1/2 h-bar. We categorize electrons as spin 1/2 particles. So in the end, it's pretty cool to see that the particles that make up everything don't actually spin the same as we see objects do in reality. This is just a simple idea of how quantum mechanics creates something just out of the norm.